Did you know that in the vast, silent expanse of space, there's a planet where it rains glass sideways? Or that astronauts returning from space sometimes report a mysterious, otherworldly smell clinging to their suits? The universe isn't just strange, it's downright surreal, and every discovery we make only deepens the mystery. Welcome to a journey where reality outshines the wildest science fiction, where the cosmos serves up wonders that defy logic and ignite our imagination. Think about this: we've sent robots to Mars, snapped photos of black holes, and even listened to the eerie hum of interstellar space. Yet, for every question we answer, a dozen more emerge, each more baffling than the last. From stars that sing to moons hiding oceans of alien water, space is a treasure chest of the bizarre, and today we're cracking it wide open. You're about to uncover 30 of the most mind-bending, head-scratching, and downright unbelievable facts about space exploration, each one proof that the universe loves keeping us guessing. This isn't just a list, it's an invitation to marvel at how little we truly know. Every rocket launch, every distant probe, every flicker of data from the edge of our solar system peels back another layer of the cosmic onion. And the deeper we go, the more we realize space isn't just a destination. It's a living, breathing enigma, a puzzle written in stardust and radio waves. So buckle up, by the time we're done, you'll never look at the night sky the same way again. Ever noticed how astronauts seem to float effortlessly in space? Well, here's something even weirder: they come back taller. That's right, without gravity's constant pull compressing their spines, astronauts can grow up to 2 full inches while in orbit. Imagine going to space and literally outgrowing your own clothes. Here's how it happens. On Earth, gravity squishes the fluid-filled discs between your vertebrae, stacking them tightly like pancakes. But in microgravity, those discs finally get a break. They expand, stretching the spine like a coiled spring. It's not just a minor shift. Some astronauts report back pain from the sudden extra height, like their bodies are protesting the cosmic growth spurt. But don't start packing for a space vacation just to gain a few inches. The effect is temporary. Once back on solid ground, gravity takes over again, and astronauts shrink back to their original height within months. Still, this quirk raises big questions for future Mars missions or long-term space habitats. If humans spend years in space, could these spinal changes become permanent? Could astronauts return too tall for their own door frames? And it's not just about comfort, there's real science here. Studying these changes helps engineers design better spacecraft seats, suits, and even exercise routines to keep astronauts' bodies Earth-ready. Because in space, even the simplest things, like standing up straight, aren't so simple anymore. After marveling at astronauts growing taller in space, here's another bizarre lunar secret: moon dust smells like gunpowder. When Apollo astronauts returned to their lunar modules, they noticed the fine gray powder clinging to their suits had a sharp, metallic scent, almost like the aftermath of a fireworks show. But why would a world with no atmosphere, no fire, and no explosions smell like something so eerily familiar? Scientists have a few theories. One idea points to the moon's surface being bombarded by solar radiation for billions of years, which charges the dust particles electrostatically. When astronauts kicked up this dust, it clung to everything, and the act of brushing it off may have triggered tiny reactions, releasing that gunpowder-like odor. Another theory suggests the dust is packed with tiny fragments of minerals like silicon and iron, which have been oxidized or essentially rusted by constant exposure to space. When these particles interact with the moisture inside a spacecraft or an astronaut's helmet, they release a metallic tang similar to the smell of burned gunpowder. But here's the kicker: without an atmosphere to carry scents, the astronauts couldn't actually smell the moon while standing on it. The aroma only became noticeable once they brought the dust inside, where it mixed with the air. That means the moon's signature scent isn't just about the dust itself, but how it behaves when it meets human technology. This discovery isn't just a quirky footnote, it's a reminder of how alien the moon really is. Even something as simple as dirt acts completely differently than it does on Earth. And for future lunar colonists, this could pose real challenges. Breathing in that abrasive, chemically reactive dust could be harmful over time, forcing engineers to design airlocks and cleaning systems we've never needed before. So the next time you look up at the moon, remember, it's not just a silent orb in the sky. It's a world that leaves its mark right down to the strange, smoky scent it leaves behind. Imagine floating in the endless void of space, opening your mouth to scream and hearing absolutely nothing. That haunting line from sci-fi movies is shockingly accurate. In the vacuum of space, no one can hear you. Not because aliens are ignoring you, but because sound simply can't travel where there's no air, no molecules, no medium to carry those vibrations. It's not just eerie, it's a fundamental difference between Earth and the cosmos that changes everything about how we explore it. On our planet, sound waves ripple through air or water, pushing molecules together in a chain reaction until they reach your ears. But space is a near-perfect vacuum, with atoms so sparse they might as well be non-existent. A supernova could explode right next to you, and you'd experience it in total silence, at least until the shockwave vaporized you. This isn't just a fun trivia fact, it's a survival challenge. Astronauts can't rely on their ears to warn them of dangers like debris impacts or equipment failures. Instead, they depend on vibrations transmitted through their spacecraft's hull or alarms flashing on screens. Yet here's the twist: inside spaceships and stations, sound behaves almost normally. Air-filled cabins let astronauts talk, laugh, and even play musical instruments. The International Space Station hums with machinery, beeping computers, and the occasional guitar riff floating through the modules. But step outside during a spacewalk, and that familiar world of noise vanishes. Your tools could clang against the hull, your breath could roar in your helmet, but just inches away beyond that thin visor, the universe swallows every sound whole. This silence shapes how we study space too. Probes like Voyager and Juno can't record audio from distant planets. Instead, they capture electromagnetic waves and plasma vibrations, which scientists later convert into sound we can hear. Those haunting songs of Jupiter or Saturn's rings, they're not real sounds, they're data translated into something our Earth-bound brains can process. Even Mars, with its thin atmosphere, is too quiet for human ears. The Perseverance rover's microphones mostly pick up the whir of its own machinery, with the Martian wind sounding like a faint, distant whisper. So why does this matter beyond the creep factor? Because silence defines the cosmos. It reminds us that space isn't just empty, it's fundamentally alien, governed by rules that defy our Earth-born instincts. Every splash of color in a nebula, every flare from a star, happens in perfect, overwhelming quiet. And for future explorers, that means redesigning how we alert, communicate, and even experience the universe. Because out there, danger doesn't roar, it approaches in deadly, soundless stealth. Venus doesn't just break the rules, it spins them backward. While most planets in our solar system rotate counterclockwise like Earth, Venus whirls in the opposite direction, a cosmic rebel with a bizarrely slow, retrograde spin. Picture this: a single day on Venus lasts longer than its entire year. That's right, it takes 243 Earth days for Venus to complete one rotation, but only 225 Earth days to orbit the Sun. So if you lived there, you'd celebrate your birthday before you'd even finished one full day. How did Venus end up like this? Scientists have two leading theories, and both sound like scenes from an interplanetary disaster movie. The first suggests a cataclysmic collision billions of years ago, when a massive object, perhaps a protoplanet, slammed into Venus with enough force to flip its rotation or slow it to a crawl. The second theory points to gravitational tug-of-war with the Sun's thick atmosphere and tidal forces, which could have gradually braked Venus's spin until it reversed. But here's the kicker: Venus isn't just spinning backward, it's also doing it at a glacial pace. A sunset on Venus would take weeks to unfold, with the Sun creeping across the sky like a slow-motion replay. This backward spin creates some truly alien conditions. The planet's thick, toxic atmosphere whips around at hurricane speeds in a phenomenon called superrotation, meaning the air moves faster than the ground below. Imagine standing in winds so fierce they could circle the planet every 4 Earth days while the surface barely budges. And because Venus rotates so slowly, its squashed shape makes gravity slightly weaker at the poles than the equator, a quirk that could throw off future lander missions by mere fractions of a second. What's even wilder, Venus's weird rotation might hold clues about our own planet's past. If a collision did flip its axis, could Earth have suffered a similar fate early on? Or did Venus's thick atmosphere play a bigger role than we thought? Every probe we send from the Soviet Venera landers to NASA's upcoming Da Vinci mission peels back another layer of this planetary enigma. Venus isn't just Earth's evil twin. It's a cosmic lesson in how violent, unpredictable, and utterly strange planetary evolution can be. The universe might just be the ultimate bartender because floating near the heart of our galaxy, there's a cloud so massive and so boozy, it could serve the entire cosmos. Meet Sagittarius B2, a colossal molecular cloud packed with enough ethyl alcohol to fill billions upon billions of cocktail glasses. That's not science fiction, it's pure, intoxicating reality. This interstellar speakeasy stretches hundreds of light-years across and drifts near the Milky Way's core, some 26,000 light-years from Earth. Inside its swirling depths, scientists have detected vast quantities of vinyl alcohol, methanol, and most famously ethanol, the same stuff in your favorite beer or whiskey. We're talking about a cloud so dense with alcohol, it could theoretically supply every human on Earth with a lifetime supply of drinks if we could somehow bottle it. But don't start drafting your intergalactic brewery business plan just yet. The alcohol here isn't floating around as a liquid ready to pour. Instead, these molecules are spread thin across the vacuum of space, mixed with other cosmic ingredients like hydrogen and dust. The sheer scale is what boggles the mind. Sagittarius B2 contains enough ethanol alone to fill 400 septillion pints. That's a 4 followed by 23 zeros, a number so big it defies earthly comparison. So how did this celestial happy hour come to be? It's all about chemistry in the cold, dark reaches between stars. When massive stars die, they spew elements like carbon and oxygen into space. Over eons, these atoms latch onto dust grains, reacting with hydrogen to form simple molecules. Given enough time and the right conditions, those molecules grow more complex, eventually becoming the organic compounds we detect today. Sagittarius B2 is essentially a galactic distillery, brewing alcohol on a mind-blowing scale through nothing more than patience and cosmic physics. Here's the kicker: clouds like this might hold clues to life itself. Ethanol isn't just for partying, it's a building block for even more complex organic molecules, the kind that could seed planets with the ingredients for biology. Some scientists speculate that similar clouds drifting through young star systems may have delivered the precursors to Earth's early oceans, setting the stage for life to emerge. Of course, this cosmic bar has some unique features. The temperatures hover near absolute zero, and the drinks are laced with toxic compounds like cyanide. Plus, the cloud's sheer size means any theoretical space traveler flying through it wouldn't even notice the alcohol, just a faint, ghostly whisper of molecules against their hull. But the existence of Sagittarius B2 reminds us that the universe is far stranger and more creative than we often assume. Who knows, maybe somewhere out there, another civilization is staring up at their night sky, pondering the giant, floating brewery in the cosmos, and raising a glass to the wonders we've yet to discover. We think of the sun as that bright, familiar disk in the sky, but peel back its fiery layers and you'll find a beast so massive, it defies earthly comprehension. At its heart lies a nuclear furnace so vast, 1.3 million Earths could squeeze inside it. Let that sink in for a moment. Every mountain, every ocean, every city on our planet reduced to a speck, repeated over 1 million times just to fill the sun's core alone. This cosmic powerhouse runs on nuclear fusion, a process so intense it turns 600 million tons of hydrogen into helium every single second. Imagine the energy of 1 billion atomic bombs detonating at once. Now imagine that happening non-stop for billions of years. That's the sun's core, but here's the twist. All that mind-blowing energy doesn't just zip straight to the surface. Instead, it embarks on an epic 1,000-year journey, fighting its way through a dense soup of plasma. Picture a single photon born in the core's unimaginable heat. It doesn't race outward at light speed as you might expect. Instead, it bounces like a pinball, colliding with atoms in the radiative zone, getting absorbed and re-emitted over and over. By the time it reaches the convective zone near the surface, it's hitched a ride on currents of bubbling plasma, rising like molten lava in a slow-motion fountain. Only then does it finally break free as sunlight, a beam that reaches Earth in just 8 minutes, after spending millennia trapped inside its own star. This time lag means the sunlight warming your skin today was forged in the sun's core around the time humans were inventing written language. It's a staggering reminder of scale. Our star isn't just big, it's deep, layered, and almost inconceivably patient. And while we see the sun as a steady, unchanging light, its core is a riot of chaos and transformation, where atoms fuse under pressures that would crush a spaceship into a speck smaller than a grain of sand. Here's what's even wilder. Despite its enormity, the sun is actually pretty average as stars go. There are red giants out there with cores that could swallow our entire solar system. Yet without this specific, carefully balanced furnace, not too big, not too small, Earth would never have gotten the steady, gentle light needed for life to evolve. So the next time you feel sunlight on your face, remember, you're touching energy that began its journey when woolly mammoths still walked the Earth, a cosmic inheritance from the heart of a star that's forever rewriting the laws of scale. Mercury plays by its own rules when it comes to timekeeping, bending our earthly concepts of days and years into something almost unrecognizable. While Earth spins smoothly on its axis every 24 hours, Mercury performs a cosmic dance so lopsided, 1 full day lasts nearly 2 of its own years. Imagine watching the sun crawl across the sky, taking 88 Earth days just to rise and set, only to realize you'd have to wait another 88 to see it happen again. That's the reality of Mercury's bizarre rotation, where a single solar day stretches longer than most Earth seasons. The secret lies in Mercury's peculiar spin-orbit resonance. For every 2 trips around the sun, the planet completes exactly 3 rotations on its axis. This precise rhythm creates a gravitational lockstep with the sun, slowing Mercury's spin to a crawl while its orbit remains blisteringly fast. Picture a dancer twirling slowly in place while whipping around a ballroom at breakneck speed. The result is a day that defies intuition. But here's where it gets even weirder. If you stood on Mercury's surface, the sun wouldn't move steadily across the sky as it does here. Instead, it would pause, backtrack, and even loop in places, creating surreal double sunrises in some locations. That's because Mercury's elliptical orbit causes its speed to vary dramatically while its rotation stays steady. When the planet zooms closest to the sun, its orbital velocity outpaces its spin, making the sun appear to reverse course temporarily. It's like watching a cosmic time lapse with the playback button stuck on erratic. This extreme environment leads to temperature swings that could vaporize metal. Daylight lasts so long that surface temperatures soar to 800 degrees Fahrenheit, hot enough to melt lead, while the endless nights plunge to nearly 300 degrees below zero. Any spacecraft landing there would need to survive not just the heat or cold, but the whiplash between them over epochs-long days. Yet Mercury's strange chronology isn't just a planetary oddity, it's a clue to the violent history of our solar system. Scientists think a colossal impact billions of years ago might have knocked Mercury into its slow spin, leaving it vulnerable to the Sun's gravitational bullying. Every probe we send, like NASA Messenger, uncovers new layers of this puzzle, revealing how a world so small can rewrite the rules of time itself. So the next time you glance at a clock, remember, elsewhere in the cosmos, a day isn't just 24 hours. Sometimes it's a lifetime. Humanity has sent its own message in a cosmic bottle, literally. Aboard both Voyager spacecraft, now hurtling through interstellar space, lie the golden records, golden-plated phonograph discs packed with sounds and images from Earth, designed to outlast our civilization and possibly greet intelligent life from another world. These aren't just random snapshots, they're a carefully curated time capsule, a love letter to the cosmos crafted by a team led by Carl Sagan. The records contain a dizzying array of Earth's essence: thunderstorms, chirping crickets, a mother's first words to her newborn, even the furious clatter of a jackhammer. There's music spanning continents and centuries, from Bach's Brandenburg concertos to Chuck Berry's Johnny B. Good. Want to hear a Peruvian wedding song or the haunting melodies of a Navajo night chant? They're there, but it's not just about sound. Etched onto the records are diagrams of human DNA, mathematical constants, and over 100 images: sunsets, cityscapes, a woman biting into an apple, even an X-ray of a human hand. Sagan's team made deliberate choices to ensure any hypothetical aliens could decode these artifacts. The record's covers feature engraved instructions in symbolic language, a pulsar map pointing back to Earth, along with a stylus and a diagram showing how to play it at the correct speed. Every element, from the uranium sample whose decay rate could date the record to the selection of a laughing child, aimed to portray humanity honestly, not just our achievements but our joys, struggles, and curiosities. What's striking is how the records avoid politics, war, or any hint of earthly conflict. Instead, they focus on what connects us: music, laughter, the natural world. As Sagan put it, they represent a gift to the possible future. Whether they'll ever be found remains unknown. Space is vast, and the Voyager's paths won't come near another star for tens of thousands of years. But for now, these golden disks drift endlessly, carrying the whisper of a species that once looked up at the stars and dared to say, "We were here." If a cosmic speedometer existed, neutron stars would break it. These stellar corpses, born from the explosive deaths of massive stars, spin so fast they could complete 600 full rotations in the time it takes you to read this sentence. Picture a blender whirling at hyperspeed, but instead of crushing ice, it's pulverizing the very fabric of matter itself. That's the dizzying reality of a neutron star's rotation, where the laws of physics get stretched to their absolute limits. What makes this even more incredible is what's spinning. A celestial object so dense, a single teaspoon of its material would weigh 1 billion tons on Earth. When a massive star collapses in a supernova, its core doesn't just shrink, it implodes with such ferocity that protons and electrons fuse into neutrons, packing the mass of an entire sun into a sphere no wider than Manhattan. The result, a neutron star's gravity is strong enough to bend light around its equator, creating a lensing effect that would make the horizon appear to curve upward if you stood on its surface. Not that you could, you'd be flattened into a subatomic pancake instantly. But how does something so heavy spin so fast? It's all about conservation of angular momentum, the same principle that makes a figure skater spin faster when they pull in their arms. When the original star collapses from millions of miles across to just 12 miles wide, that rotation accelerates exponentially like a cosmic top wound up by gravity itself. Some newborn neutron stars, called pulsars, beam radiation from their poles like interstellar lighthouses, their rapid spins creating pulses so regular they rival atomic clocks. The Crab pulsar, for instance, flashes 30 times per second with such precision, you could set your watch by it across 1,000 light years. Here's where it gets truly surreal. Neutron stars don't just bend space and time, they crack their surfaces. The crust, a crystalline lattice of iron nuclei under unimaginable pressure, occasionally starquakes, releasing energy equivalent to a magnitude 32 earthquake. These quakes can abruptly change the star's spin speed, like a record skipping on a turntable made of pure gravity. Meanwhile, the interior may contain exotic states of matter we can't recreate on Earth: hyperfluid neutrons, superconducting protons, or even free-floating quarks swimming in a quantum soup. The existence of neutron stars forces us to rethink what matter can do under extreme conditions. They're natural laboratories for physics we can't replicate, cosmic artifacts that prove the universe isn't just stranger than we imagine, it's stranger than we can imagine. And somewhere out there, one of these mind-bending objects is spinning silently in the dark, completing another revolution before your next heartbeat. Deep in the constellation Cancer, orbiting a star 40 light-years away, there's a world that would make even a billionaire blush. Meet 55 Cancri E, a planet so rich in carbon, scientists believe a significant chunk of its interior could be solid diamond. That's right, an entire celestial body potentially glittering with crystallized carbon, crushed into gemstone perfection by pressures beyond human comprehension. This isn't just a sparkling hypothetical. 55 Cancri E is a super-Earth, about twice our planet's size but 8 times as massive, with a surface temperature hot enough to melt steel. Its parent star bathes it in so much radiation that years there last just 18 Earth hours, and its surface might be a bubbling ocean of lava. But beneath that hellish exterior, something extraordinary lurks. The planet's composition is carbon-heavy, meaning its core could contain layers of diamond hundreds or even thousands of miles thick. Imagine Earth's mantle replaced with a gemstone the size of a continent, forged not in jewelry shops but in the furnaces of cosmic physics. So what's this diamond planet worth? Forget numbers, it's literally incalculable. Even if we could mine it, which we can't, unless we invent lava-proof spaceships, flooding the market with that much diamond would instantly make the gemstone as common as sand. But here's the twist: 55 Cancri E's real value isn't in its bling. It's a laboratory for understanding how extreme pressure reshapes matter. On Earth, diamonds form about 100 miles underground, where carbon atoms are squeezed into crystalline structures. On this exoplanet, the crushing weight of its own atmosphere could have created diamond layers stretching to the core, a phenomenon we've never witnessed up close. The existence of such a world forces us to rethink planetary diversity. Most planets in our solar system, like Earth or Mars, are silicate-rich, basically made of rock. But 55 Cancri E belongs to a rare class of carbon planets, where carbon outcompetes oxygen as the dominant element. In theory, these worlds could have mountains of graphite, rivers of tar, and skies thick with carbon-based smog. Some scientists speculate that if life existed there, it might be built on entirely different chemistry, silicon-based organisms breathing carbon monoxide, perhaps. Of course, we'll never stroll on 55 Cancri E's diamond-studded surface. Its conditions are lethally inhospitable, and even if we could reach it, mining would be like trying to extract ice from an active volcano. But the planet's sheer audacity reminds us that the universe specializes in the unimaginable. Out there, in the infinite variety of exoplanets, there could be worlds made of ruby, sapphire, or substances we haven't even named yet. 55 Cancri isn't just a cosmic jewel, it's a glimpse into how strange, dazzling, and downright extravagant planetary formation can get when given the right ingredients and a few billion years to cook. The Hubble Space Telescope nearly became history's most expensive flop until a pair of glasses fixed its cosmic blur. When NASA launched Hubble in 1990, scientists expected razor-sharp images of distant galaxies. Instead, the world got photos so fuzzy, they looked like they'd been taken through a windshield smeared with Vaseline. The culprit, a mirror polished to near perfection but shaped wrong by just 2 microns, roughly the thickness of a bacterium. That microscopic error scattered starlight, turning what should have been celestial masterpieces into frustrating blurs. Public outrage was swift. Late-night hosts mocked Hubble as a $2 billion blunder. Congress grilled NASA officials, and headlines declared the telescope a national embarrassment. But behind the scenes, engineers were already devising a fix as audacious as the flaw itself. They'd send astronauts to outfit Hubble with corrective optics, essentially cosmic contact lenses. The 1993 repair mission became one of NASA's most high-stakes endeavors, requiring spacewalking crews to install the COSTAR system, Corrective Optics Space Telescope Axial Replacement, a refrigerator-sized unit packed with tiny mirrors designed to counteract Hubble's distortion. The operation unfolded like a zero-gravity ballet. Over 5 tense days, astronauts performed grueling spacewalks, swapping out instruments and snapping COSTAR into place. One wrong move could have doomed the telescope forever, but when the first corrected images streamed back to Earth, the world gasped. Distant stars snapped into pinpoints. Nebulae revealed intricate filaments of gas. Suddenly, Hubble's vision was 20 times sharper, unlocking secrets from the age of galaxies to the existence of dark energy. What's astonishing isn't just that the repair worked, it's how perfectly it transformed Hubble's destiny. Those corrective optics turned a laughingstock into humanity's most powerful eye on the cosmos, capturing iconic images like the Pillars of Creation and the Hubble Deep Field. Later upgrades replaced COSTAR with built-in corrected instruments, but the legacy of that daring fix endures. Hubble taught us more than astronomy. It proved that even our mightiest tools can fail, and that ingenuity can redeem them. The blur that almost broke NASA became the catalyst for a golden age of discovery, reminding us that in space exploration, setbacks aren't endings. They're just problems waiting for the right humans armed with the right wrenches to solve them. For over 400 years, Jupiter's Great Red Spot has been the solar system's most enduring storm, a churning maelstrom so vast 3 Earths could fit side by side within its crimson swirls. Yet this iconic tempest, once the undisputed king of planetary weather, is quietly losing its crown. Recent observations reveal the storm has been shrinking for decades, its winds slowing, its once oval shape collapsing into a narrower, more disorganized mess. What was once a roaring hurricane the size of a planet is now more like a fading echo of its former self. The Great Red Spot's history reads like a cosmic mystery novel. First glimpsed in the 1600s by astronomers like Giovanni Cassini, it's raged non-stop ever since, fueled by Jupiter's chaotic atmosphere. Unlike Earth storms, which die out in days when they hit land or cold water, Jupiter's mega-hurricane has no solid surface to sap its energy. Instead, it feeds on the gas giant's turbulent jet streams, drawing power from deeper layers of hydrogen and helium. At its peak, wind speeds topped 400 miles per hour, enough to shred a spacecraft like tissue paper. But since the late 1800s, when scientists began systematic measurements, the storm's borders have steadily retreated. In the 1970s, Voyager probes showed it spanned 14,000 miles, wide enough to swallow Earth whole. By 2014, Hubble images revealed it had slimmed to just 10,000 miles across. Some models suggest it could vanish entirely within our lifetimes, its towering ammonia clouds dissolving into Jupiter's endless sky. Why the slow fade? Theories abound. One camp argues Jupiter's changing wind patterns are starving the storm like a fire running out of oxygen. Others point to smaller vortices, mini-storms, colliding with the Great Red Spot and stealing its energy. There's even speculation that the storm's core might be unraveling from within, its legendary stability finally succumbing to entropy. Yet for all its decline, the Great Red Spot still dwarfs anything Earth could muster. Its roots plunge 200 miles below Jupiter's cloud tops, deeper than our deepest ocean trenches. And while it's shrinking vertically too, it remains taller than Mount Everest by orders of magnitude. Even in retreat, it's a reminder of nature's capacity for extremes, a tempest that outlasted empires, now whispering its final act across the cosmos. Whether it vanishes or stabilizes, its legacy is secure. The longest-running show in the solar system, a swirling testament to the raw, untamed power of planetary weather. Astronauts floating aboard the International Space Station face a problem most of us never consider. Every drop of water is precious. With no rivers, rain, or grocery stores in orbit, the ISS relies on an ingenious but eyebrow-raising solution, turning sweat, breath moisture, and yes, even urine, back into clean drinking water. It might sound like something out of a dystopian sci-fi novel, but this high-tech recycling system is the reason astronauts stay hydrated without constant resupply missions from Earth. Here's how it works. The Environmental Control and Life Support System, or ECLS, captures every possible source of moisture on board, condensation from the air, collected water vapor from astronaut breath scooped up. Even the sweat beading on their skin during a workout gets funneled into the system. But the real star, or perhaps the most notorious component, is the urine processor assembly, which takes liquid waste and distills it into purified H2O through a series of filters and chemical treatments so advanced, the end product is cleaner than most tap water on Earth. Now, before you grimace, consider the numbers. Transporting just 1 gallon of water to the ISS costs roughly $20,000. With a crew of 6 astronauts needing about 1,000 gallons a year, recycling is the only practical way to sustain long-term missions. The system reclaims over 90% of the station's water, turning what would be waste into a vital resource. Astronauts themselves often joke about the process, with some admitting the mental hurdle is harder than the science. After all, sipping yesterday's coffee is one thing, but knowing it passed through a filter that handled urine takes some getting used to. The technology behind this isn't just impressive, it's essential for humanity's future in space. Plans for lunar bases or Mars missions hinge on perfecting these closed-loop systems where every molecule gets reused. Scientists are even experimenting with recycling water from laundry, yes, that too, and growing plants that can purify wastewater through natural processes. So while the idea of drinking recycled urine might make some squeamish, it's a reminder that survival in space demands creative solutions, ones that push us past earthly hang-ups and into a future where sustainability isn't just ideal but inevitable. After all, in the void between worlds, there's no room for waste. Just ask any astronaut. When you're floating 250 miles above the nearest sink, you learn to appreciate every drop. Mars flips the script on one of Earth's most familiar sights. Sunsets aren't fiery red there. They're an eerie, cool blue, while our skies blaze with oranges and pinks as the sun dips below the horizon. The Curiosity rover has captured Martian sunsets that look like something from a sci-fi film, a pale blue disk fading into a dusky lavender sky. This surreal color swap isn't just artistic license, it's a masterclass in atmospheric physics, proving how tiny particles can paint an entire world's palette. The secret lies in the dust specifically, how fine Martian particles interact with sunlight. Earth's sunsets turn red because our thick atmosphere scatters shorter blue wavelengths, leaving longer red ones to dominate at dawn and dusk. But Mars's thin, carbon dioxide-rich air is choked with ultrafine dust, and these particles are just the right size to do the opposite. They let red light slip through while scattering blue light sideways, like a celestial prism filtering the sun's rays. The effect is strongest when the sun is low, concentrating that otherworldly azure glow around the solar disk itself. Curiosities' time lapses of these blue sunsets aren't just pretty, they're scientific gold mines. By analyzing the light's intensity and color, researchers can track seasonal dust storms, measure atmospheric density, and even predict weather patterns. During global dust events, when the sky turns into a perpetual tan haze, the blue effect intensifies, revealing how particles migrate and settle across the planet. It's a reminder that Mars's atmosphere, though wispy compared to Earth's, is dynamic enough to sculpt daily phenomena we'd barely recognize. Imagine standing in Gale Crater as the sun vanishes behind the rim. The temperature plummets, shadows stretch like ink, and that blue halo lingers like a ghostly afterimage. There's no crickets chirping, no breeze rustling, just silence and a sky that defies every sunset you've ever known. For future Mars colonists, this might become routine, but for now, it's a dazzling quirk of planetary science, proof that even the simplest things like watching the day end can feel alien when you're 50 million miles from home. Saturn's rings aren't just stunning, they're vanishing right before our eyes. Gravity is slowly but relentlessly pulling them down onto the planet in a shimmering cosmic rain. At a rate so precise it's been measured as one Olympic-sized swimming pool's worth of material every hour. That means the same rings Galileo first glimpsed through his telescope in 1610 could be gone in a cosmic blink, perhaps as little as 100 million years from now. For a planet that's 4.5 billion years old, that's practically tomorrow. The process, called ring rain, works like an invisible celestial vacuum. Saturn's magnetic field tugs on the tiny ice and rock particles that make up the rings, charging them and guiding them along magnetic lines down into the planet's upper atmosphere. As they fall, they vaporize, creating a surprising drizzle of charged water molecules that NASA Cassini probe detected during its final, daring orbits. This isn't some gentle mist, it's a torrential downpour by cosmic standards, with enough material falling every second to fill a dozen boxcars. Over eons, this steady drain is literally erasing Saturn's most famous feature. But why now? Saturn's rings likely formed relatively recently, perhaps just a few 100 million years ago when dinosaurs still roamed Earth. One theory suggests they're the shattered remains of a moon or comet that strayed too close and was torn apart by Saturn's gravity. If that's true, we're witnessing a transient cosmic spectacle, a fleeting masterpiece in the grand timeline of the solar system. Other gas giants like Jupiter and Neptune have faint, dusty rings, but none rival Saturn's brilliance precisely because they've already lost most of their material to the same relentless pull. What's fascinating is how delicate the balance really is. The rings stretch over 280,000 miles across, yet they're barely thicker than a skyscraper is tall. If you shrank Saturn to the size of a basketball, its rings would be 10,000 times thinner than a sheet of paper. This fragility makes them vulnerable to more than just gravity. Solar radiation and micrometeoroid impacts constantly chip away at them, scattering particles into space or sending them spiraling toward Saturn's cloud tops. The countdown has already begun. By the time Earth's next major ice age comes and goes, Saturn's rings might be a shadow of their former glory. Future astronomers could gaze through telescopes and see only faint, broken arcs like the ruins of a celestial cathedral. It's a humbling reminder that even the grandest features of our solar system are temporary, and that we're lucky enough to live in the brief window when Saturn still wears its crown. Deep in the orbiting laboratories of the International Space Station, scientists have conjured temperatures so cold they defy earthly comparison, reaching a mind-numbing 1/1000th of a degree above absolute zero. That's colder than the void between galaxies, colder than the afterglow of the Big Bang, even colder than nature can produce on its own. This record-breaking chill isn't just for bragging rights, it's the key to unlocking quantum mysteries that could revolutionize technology as we know it. The magic happens inside NASA's Cold Atom Lab, a suitcase-sized device that's essentially the universe's most sophisticated freezer. Using lasers and magnetic fields, it slows atoms to a near standstill, stripping away their thermal energy until they're barely moving at all. At these extremes, matter stops behaving like the solid stuff we know and enters a bizarre quantum state called a Bose-Einstein condensate, where atoms lose their individual identities and merge into a single, wave-like superatom. It's like watching a crowd of dancers suddenly move in perfect unison, as if governed by an invisible rhythm. Why do this in space? Earth's gravity constantly tugs on these fragile quantum states, limiting how long scientists can study them before they collapse. But in the microgravity of the ISS, researchers can observe these condensates for up to 10 seconds at a time, an eternity in quantum physics. Those extra seconds let them probe phenomena like superfluidity, where fluids flow without friction, or simulate how matter behaves near a black hole's event horizon. The implications are staggering. Mastering matter at these temperatures could lead to ultra-precise quantum sensors for navigation, unhackable quantum communication networks, or even superconductors that work at room temperature, materials that could transform energy grids and medical imaging. Already, the Cold Atom Lab has created exotic states of matter never before observed, like atomic bubbles, where atoms arrange themselves on the surface of a sphere. What's poetic is how this icy frontier sits just 250 miles above our heads, aboard a station bathed in sunlight hot enough to melt steel. The Cold Atom Lab proves that the universe's most extreme conditions aren't always out among the stars. Sometimes we create them ourselves, floating in orbit, rewriting the rules of physics one frozen atom at a time. A speck of paint doesn't sound dangerous until it's hurtling through space faster than a bullet. At 17,500 miles per hour, even a fleck the size of a grain of sand becomes a deadly projectile, packing the kinetic energy of a bowling ball dropped from a skyscraper. That's the terrifying reality of orbital debris, a growing cloud of space junk that turns Earth's orbit into a cosmic shooting gallery. From defunct satellites the size of school buses to fragments of exploded rocket stages, millions of man-made objects zip around our planet, each one a potential disaster waiting to happen. The numbers are staggering. Over 25,000 tracked objects larger than 4 inches currently orbit Earth, along with countless smaller, untraceable fragments. Every time two objects collide, like the infamous 2009 crash between a defunct Russian satellite and an active American one, they shatter into thousands of new pieces, fueling a cascading chain reaction known as the Kessler syndrome. Picture a high-speed domino effect where each collision spawns more debris, increasing the odds of future impacts until entire orbital highways become impassable. What makes space junk uniquely hazardous isn't just its speed, it's the math. At those velocities, a 1 centimeter wide bolt strikes with the force of an exploding hand grenade. The International Space Station regularly performs debris avoidance maneuvers, firing thrusters to dodge incoming threats, but not everything can be tracked. In 1983, the Space Shuttle Challenger returned from mission STS-7 with a quarter-inch pit in its windshield, likely caused by a paint chip. Had that impact occurred a few millimeters to the side, it could have cracked the entire window, risking catastrophic depressurization. The solutions are as complex as the problem itself. Engineers are testing nets, harpoons, and even laser brooms to sweep debris from orbit, while new satellites are designed to deorbit themselves at the end of their lifespans, burning up harmlessly in the atmosphere. Private companies now offer space tow truck services to remove dead satellites, and international guidelines push for responsible disposal. But with commercial spaceflight booming, the junk pile keeps growing. For astronauts, space debris adds a constant undercurrent of danger. During spacewalks, even a stray screw could puncture a suit, and mission controllers keep meticulous radar logs of orbital traffic, calculating collision risks down to fractions of a second. The stakes couldn't be higher. A single catastrophic impact could litter popular orbits with shrapnel, rendering them unusable for generations. Imagine if the shipping lanes of the sea were suddenly clogged with invisible, hyper-fast shards of metal. That's the future we're racing to avoid. So while we gaze up at the stars and dream of exploration, there's an invisible threat circling overhead, a reminder that humanity's reach into space comes with responsibilities. The same ingenuity that launched satellites must now clean up after them, because in the final frontier, there's no such thing as out of sight, out of mind. Every bolt, every panel, every lost wrench up, there is a bullet in a gun we can't afford to fire. The moon may seem like a constant fixture in our night sky, but it's quietly slipping away at the glacial pace of 1.5 inches every year. That barely seems like enough to notice, but over the span of cosmic time, it adds up to something monumental. The reason Earth's oceans are fighting a slow-motion tug of war with our lunar neighbor. Every time the moon's gravity pulls on Earth, it doesn't just create tides, it drags those bulges of water ever so slightly ahead of the moon's position. This creates a gravitational push, transferring energy from Earth's rotation to the moon's orbit. Think of it like a cosmic game of crack the whip. As Earth's spin slows down, the moon gets flung farther out. The numbers are staggering. 4 billion years ago, the moon loomed 10 times larger in the sky, and Earth days were just 18 hours long. Fast forward another few billion years, and the moon will be distant enough to no longer fully eclipse the sun, robbing future civilizations of total solar eclipses altogether. But the real drama kicks in when you consider what happens to Earth without its lunar anchor. The moon stabilizes our planet's axial tilt, keeping our seasons relatively predictable. Without it, Earth's axis could wobble chaotically. Imagine winters so extreme they last decades, or summers that scorch continents into deserts. Mars, with its puny moons, experiences wild swings in tilt over millions of years, and without our moon, Earth could suffer the same fate. Days would shrink too, as the braking effect of the tides vanishes, eventually spinning so fast that hurricanes become permanent fixtures, and the planet's shape bulges at the equator like a cosmic top spinning out of control. Yet this slow retreat isn't just a doomsday clock. It's a natural record of Earth's history. Apollo astronauts left mirrors on the moon's surface, and by bouncing lasers off them, scientists measure the exact distance to the millimeter. Those reflections confirm not just the moon's drift, but also that gravity itself behaves precisely as Einstein predicted over cosmic distances. So while we won't miss the moon in our lifetimes, its gradual departure is a reminder. Even the grandest celestial dances are fleeting. The same tides that shape our coastlines today are writing an epitaph for Earth's future, one where the night sky grows lonelier with each passing year. In 1967, the Soviet Union launched a satellite called Cosmos 1267, a seemingly ordinary mission until scientists made a jaw-dropping discovery years later. Hidden inside its dormant metal shell were colonies of bacteria, still alive after surviving the vacuum of space, brutal temperature swings, and relentless cosmic radiation. These weren't extremophiles engineered for space travel, they were common Earth bacteria, accidental stowaways that had clung to the satellite before launch. Somehow, they defied every expectation of life's limits, rewriting the rules of biology in the process. The bacteria belonged to a hardy genus called Streptococcus, the same family responsible for human ailments like strep throat. No one expected them to last more than a few days in orbit, let alone the years they endured. When researchers finally opened the satellite's sterilized interior after its return to Earth, they found the bacteria not just alive but thriving. They had entered a dormant state, essentially pressing pause on their metabolism until conditions improved. a survival tactic so effective it mimicked suspended animation. What makes this discovery even more astonishing is the environment they survived in. Space is merciless. Temperatures swing from hundreds of degrees below zero to scorching heat in sunlight, while ultraviolet radiation shreds DNA like confetti. Yet these bacteria hunkered down in microscopic nooks, shielded by layers of metal and perhaps even their own dead brethren, forming a makeshift barrier against the void. Scientists suspect their resilience came from a combination of dehydration, effectively freeze-drying themselves, and an ability to repair DNA damage once reintroduced to moisture. This accidental experiment forced biologists to rethink life's boundaries. If common bacteria could endure years in space, what else might survive? Could microbes hitchhike on asteroids or comets, seeding life across the cosmos? The idea, called panspermia, suddenly seemed less like science fiction and more like a plausible pathway for life's spread. Even more pressing, were we contaminating other worlds with Earth's microbes every time we sent a probe? NASA and other agencies now meticulously sterilize spacecraft, but Cosmos 1267 proved that even the strictest protocols might miss something. The satellite's legacy lives on in modern astrobiology research. Scientists now intentionally expose microbes to space on platforms like the International Space Station, testing their limits in experiments like ESA's exposed missions. Some bacteria, like the radiation-resistant Deinococcus radiodurans, can survive years in open space, bolstering theories that life might persist on Mars or Europa. Others, like tardigrades, tiny water bears, can even reproduce after cosmic exposure, adding another layer to the mystery of life's tenacity. Cosmos 1267 bacteria didn't just survive, they opened a cosmic Pandora's box. If life can cling to existence in the harshest corners of space, then perhaps nowhere is truly sterile. The universe might be far more hospitable or far more contaminated than we ever imagined. And those unassuming Soviet microbes, they became unintentional pioneers, proving that life, once it takes hold, refuses to go quietly, even in the dead of space. Pluto takes the concept of a long year to staggering new heights. One orbit around the Sun lasts 248 Earth years. That means if you celebrated your first birthday on Pluto the day you arrived, you'd need to live another 2.5 centuries just to blow out the candles again. Even more mind-bending, since its discovery in 1930, Pluto hasn't even completed a third of its journey around the Sun. The reason for this cosmic slow dance lies in Pluto's extreme distance from the Sun, about 40 times farther out than Earth. Out in the frigid outskirts of the solar system, where sunlight is barely 1,000th as strong as what we experience, gravity's grip weakens dramatically. Planets and dwarf planets like Pluto move slower the farther they are from the Sun's pull, following Kepler's laws of planetary motion. It's like a merry-go-round where the outer horses barely crawl compared to the ones near the center. But Pluto's orbit isn't just slow, it's chaotic. Unlike Earth's nearly circular path, Pluto follows an elongated ellipse so extreme that at its closest approach, it actually dips inside Neptune's orbit for 20 years out of every 248. This wild swing brings dramatic seasonal changes. When NASA's New Horizons probe flew by in 2015, it caught Pluto at the tail end of its summer, with nitrogen ice sublimating into a wispy atmosphere that will refreeze over the next century as Pluto retreats from the Sun. Imagine standing on Pluto's surface. The Sun, a mere pinprick in the sky, provides little warmth, casting long shadows over icy plains and nitrogen glaciers. Seasons don't change in months, they unfold over decades. A single winter could last more than a human lifetime, with temperatures plunging to nearly 400 degrees below zero. Even Pluto's own moon, Charon, hovers motionless in the sky, tidally locked in a perpetual dance where both worlds always show the same face to each other. What's truly humbling is how Pluto's timescale dwarfs human history. The last time Pluto was in its current position, the Industrial Revolution had barely begun. By the time it completes one full orbit, our species might have colonized other star systems or vanished altogether. This slow celestial rhythm reminds us that the cosmos operates on a clock we can scarcely fathom, where even a dwarf planet's leisurely stroll is a marathon spanning generations. So the next time you complain about a long year, remember, on Pluto you wouldn't even have lived long enough to complain once. The Milky Way has a secret: it smells like a cosmic distillery. Astronomers probing the vast gas clouds near the center of our galaxy made a startling discovery. Floating among the stars is ethyl formate, the very same compound that gives raspberries their sweet, fruity aroma and rum its rich, enticing edge. That's right, our galaxy's core isn't just a chaotic swirl of dust and gas. It's laced with the essence of interstellar jam and an otherworldly liquor cabinet. This revelation came from radio telescopes trained on Sagittarius B2, a massive molecular cloud packed with organic molecules. By analyzing the unique wavelengths of light absorbed and emitted by these compounds, scientists identified ethyl formate's unmistakable chemical fingerprint. It wasn't just a trace amount either. Enough of this aromatic molecule drifts between the stars to fill a billion bottles of raspberry-flavored rum, if such a thing could ever be bottled. But how does a galaxy develop a sweet tooth? The answer lies in the complex chemistry of space itself. When stars are born, they churn out heavy elements like carbon and oxygen, which later bond with hydrogen to form alcohols, esters, and other flavorful compounds. These molecules hitch rides on dust grains, swirling for eons until they're swept up into new clouds or incorporated into forming planets. Ethyl formate isn't alone out there. Astronomers have also found vinyl alcohol, glycolaldehyde, a sugar precursor, and even acetic acid, the main component of vinegar. Taken together, the Milky Way's core might smell like some bizarre interstellar fruit salad left to ferment in the void. Of course, you wouldn't actually catch a whiff of rum if you could float through these clouds. Space is a near-perfect vacuum, so there's no air to carry scents to your nose. Even if you could breathe it in, the ethyl formate is spread so thin that your senses wouldn't register it. Not to mention the cloud's other inhabitants like hydrogen cyanide and sulfur compounds would likely overpower any pleasant aromas with the stench of burnt almonds and rotten eggs. Yet this discovery is more than just a quirky fun fact. Ethyl formate and its molecular cousins are building blocks for life's essential compounds. Finding them in space suggests that the ingredients for flavor, fragrance, and even biochemistry might be scattered throughout the cosmos, waiting to be incorporated into new worlds. Who knows, maybe somewhere in the galaxy, a distant planet's oceans are infused with the faintest hint of raspberry, or its rain carries the subtle bouquet of interstellar spirits. For now, we're left with a delicious irony that the same molecules that delight our senses on Earth also drift endlessly in the darkness between the stars. The universe isn't just vast and violent, it's capable of brewing up flavors and scents that feel strangely, wonderfully familiar. So next time you sip rum or bite into a raspberry, remember, you're tasting a little piece of the Milky Way's hidden recipe. In space, even tears refuse to fall. Without gravity to pull them downward, astronauts' tears don't stream down their cheeks. They pool into shimmering, floating bubbles right on their eyeballs. It sounds almost poetic until you realize those liquid globes don't go anywhere. They cling stubbornly, growing larger until they either blur vision or spill over in an awkward, stinging wave. Forget the dramatic movie moments. Crying in microgravity is more like getting soap in your eyes during a car wash. The science behind this is as fascinating as it is uncomfortable. On Earth, tears spread evenly across the eye's surface, then drain through tiny ducts into your nasal cavity. But in zero gravity, surface tension rules, turning every tear into a rebellious globe that refuses to move unless manually wiped away. Some astronauts report the sensation feeling like a persistent, watery lens glued to their cornea, while others describe the saltiness causing a burning sensation that lingers far longer than on Earth. And if you think rubbing your eyes helps think again, with no gravity to pull the fluid away, you're just smearing the problem around. This quirk isn't just a minor inconvenience, it's a genuine hazard during critical tasks. Imagine trying to dock a spacecraft or repair delicate equipment while your vision is half obscured by a wobbly tear bubble. NASA actually trains astronauts to resist rubbing their eyes, teaching them to blink rapidly instead, using their eyelids to push tears toward absorbent pads in their helmets. But even then, emotions don't always cooperate. After months in isolation, fatigue or frustration can strike, and suddenly you're blinking through what astronauts jokingly call space sadness soup. Yet there's a poignant irony here. In an environment where human bodies behave so strangely, where bones weaken, muscles atrophy, and even spines stretch, tears become a literal reflection of our earth-bound biology struggling to adapt. They're a reminder that no matter how advanced our technology, some things remain stubbornly, beautifully human. Whether it's the awe of seeing Earth from afar or the loneliness of months in isolation, space doesn't just change how we cry, it reminds us why we do. So the next time you wipe away a tear, take a second to appreciate gravity's quiet kindness, because somewhere overhead, an astronaut is blinking hard, wishing they could do the same. Saturn isn't just the ringed jewel of our solar system, it's also home to one of the most perplexing weather patterns ever discovered. At its north pole, a six-sided hurricane rages, a perfect hexagon so precise it looks like it was etched by some cosmic draftsman. This isn't a fleeting storm, it's a persistent, swirling behemoth wider than two Earths stacked side by side, with winds screaming at over 300 miles per hour. And unlike the chaotic cyclones we see on other planets, this one holds its geometric shape with eerie precision, defying every expectation of how fluids behave in nature. The hexagon was first spotted by Voyager in the 1980s, but it wasn't until Cassini's mission decades later that scientists realized it wasn't just a trick of the light. The structure plunges at least 60 miles into Saturn's atmosphere, a towering wall of clouds rotating in lockstep like some celestial gear. What's bizarre isn't just its shape, it's the stability. While hurricanes on Earth dissolve within days or weeks, Saturn's hexagon has persisted for at least 40 years, possibly much longer. The only comparable phenomenon might be Jupiter's Great Red Spot, but even that drifts and morphs. It's a polygon frozen in time. So how does a gas giant, a world without solid surfaces, conjure such geometric perfection? Theories abound, but none fully explain it. One leading idea suggests the hexagon forms because of Saturn's unique atmospheric jet streams, rivers of gas that flow at different speeds, creating shear forces that organize turbulence into geometric patterns. Picture spinning a bucket of water. Under the right conditions, the fluid inside can form stable waves. Now scale that up to planetary proportions, add layers of swirling hydrogen and helium, and you might get a hexagon. Laboratory experiments on Earth using rotating fluids have even recreated similar polygonal shapes, lending some credibility to the idea. But here's the catch. Those lab experiments only produce hexagons under very specific conditions, and Saturn's atmosphere is anything but controlled. The planet's deep internal heat, coupled with its rapid rotation, a day there lasts just 10.5 hours, creates a cauldron of chaos, yet somehow, against all odds, order emerges. Some researchers speculate deeper forces are at play, like standing waves in the atmosphere or even interactions between Saturn's magnetic field and its charged upper layers. Others wonder if the hexagon is just the visible tip of a much larger, hidden structure beneath the clouds. What's undeniable is how alien this makes Saturn feel. Hurricanes on Earth spiral into familiar curves, but this is geometry writ large, a storm that obeys laws we barely understand. future missions might unravel the mystery, perhaps by dropping probes directly into the hexagon's churning edges. Until then, it stands as a reminder that even in our own cosmic backyard, nature still has tricks up its sleeve. A planet known for its beauty hides a polar enigma, a perfect hexagon spinning silently in the dark, waiting for us to decode its secrets. Before humans ever ventured beyond Earth's atmosphere, a scrappy stray dog named Laika proved it was possible at a heartbreaking cost. In 1957, as the space race kicked into high gear, the Soviet Union launched Sputnik 2 with the mixed-breed pup aboard, making her the first living creature to orbit our planet. But while her name became synonymous with courage, her mission was never designed for a happy ending, a stark reminder of how far we've come in balancing exploration with ethics. Chosen for her calm demeanor and street-tough resilience, Laika was plucked from Moscow's alleys and thrust into a brutal training regimen. Scientists subjected her to centrifugal forces simulating rocket launches, confined her in progressively smaller cages, and even trained her to eat a special gelatinous nutrient paste, the only food possible in weightlessness. When launch day arrived, sensors tracked her racing heartbeat as the rocket roared to life, climbing toward an altitude no animal had ever reached. For a few hours, Laika became a global sensation, a living symbol of Soviet ingenuity. But behind the triumph lay a grim reality. Sputnik 2's design offered no way home. Overheated by a failed thermal system, the cabin temperatures soared past 100 degrees Fahrenheit within hours, leaving Laika no chance of survival. Soviet officials initially claimed she died painlessly after a week in orbit, but the truth only emerged decades later. She likely perished within mere hours from stress and overheating. The world's first space traveler had been doomed from liftoff, a sacrifice to political urgency and technological limits. Laika's legacy ripples through time, forcing us to confront uncomfortable questions. Early space programs viewed animals as disposable test subjects. Monkeys, mice, and dogs were routinely exposed to lethal risks without public outcry. Today, guidelines for animal testing in space are vastly stricter, prioritizing humane treatment and survival. NASA's BioSentinel mission, for instance, safely returned yeast cells and fruit flies from deep space, while modern cosmonaut dogs fly with elaborate life support systems. Yet debates persist. How much risk to animals is acceptable in the name of science? Could we have reached the stars without their silent contributions? What's often overlooked is how Laika's mission, however tragic, paved the way for human survival in space. Her voyage proved living organisms could withstand launch forces and microgravity, data that directly informed Yuri Gagarin's historic flight just 4 years later. Street-side memorials in Russia and a plaque at the Star City Cosmonaut Training Center now honor her as a pioneer, not just a casualty. Even the ship that carried her holds symbolic weight. As Sputnik 2 burned up in Earth's atmosphere 5 months later, one poet imagined it as a sarcophagus glowing like a farewell torch. The ethics of Laika's mission may never sit easily with us, but her story transcends politics. She represents both the audacity of early space exploration and its moral ambiguities, a reminder that progress often walks hand in hand with sacrifice. As we push toward Mars and beyond, her memory asks us to weigh ambition against compassion, ensuring that the creatures who helped us touch the cosmos are never forgotten. In the grand narrative of spaceflight, Laika wasn't just a passenger. She was the first Earthling to show us the stars, paying a price we can never repay. We picture the cosmos as an endless black void dotted with stars, but science paints a very different picture literally. If you could average the color of all light from 200,000 galaxies, the universe wouldn't be black or even deep blue. It would be a warm, creamy shade nicknamed cosmic latte. That's right, the universe, in all its infinite majesty, is secretly beige. This revelation came from a team of astronomers at Johns Hopkins University who analyzed the light spectra from massive galaxy surveys. They didn't just tally up stars, they accounted for every wavelength, from the fiery glow of young blue stars to the dull red embers of ancient giants. The result, a hex code #FFF8E7, that looks like the perfect cafe order. The reason for this milky hue lies in the universe's middle-aged stars which dominate the cosmic census. Most galaxies are packed with yellow and white stars like our Sun, whose combined light washes out the deeper blues and reds into something resembling a celestial cappuccino. But here's what's wild: this color hasn't always been the same. In its fiery youth, the universe leaned blue, bursting with hot, short-lived stars. Billions of years from now, as those stars die and red dwarfs become the norm, the cosmic palette will shift toward a deeper russet. We're living in the universe's beige period, a Goldilocks era where star formation has slowed just enough to create this peculiar average. Of course, you'd never actually see this color if you floated in space. Our eyes can't perceive the combined light of every galaxy simultaneously, and the darkness between stars still dominates our view. But as a statistical quirk, Cosmic Lotte flips a fundamental assumption: space isn't just absence. It's the sum of countless radiant points, a tapestry woven from every star that ever burned. What's poetic is how ordinary the universe's true color seems. After eons of cosmic violence, colliding galaxies, exploding supernova, ravenous black holes, the grand average is something you'd find in a coffee shop. Maybe there's a lesson there. Even in the infinite, there's comfort in the familiar. So next time you sip a latte, remember, you're tasting the closest thing to the color of everything. Some stars don't blaze, they barely smolder. Meet the Y-class brown dwarfs, cosmic oddballs so cool you could theoretically reach out and touch one without being vaporized. These failed stars simmer at surface temperatures below 80 degrees Fahrenheit, colder than a summer day on Earth and downright cozy compared to our Sun's 10,000-degree inferno. Picture a celestial ember the size of Jupiter, glowing faintly in the infrared, its warmth more like a campfire's dying breath than a star's fury. What makes these objects so bizarre is their identity crisis. They're too massive to be planets, yet too puny to ignite the nuclear fusion that powers true stars. Instead of shining brightly, they radiate leftover heat from their formation, fading slowly over billions of years like forgotten tea left on a cosmic countertop. The coldest known brown dwarf, WISE 0855, hovers at a frosty -10 degrees Fahrenheit, chillier than a winter night in Antarctica. If you stood on its hypothetical surface and survived the crushing gravity, you'd need a jacket more than a heat shield. But don't let their mild temperatures fool you. Brown dwarfs are laboratories of extreme physics. Their atmospheres seethe with turbulent storms larger than Earth, where clouds of molten iron and sand swirl in perpetual twilight. Some even rain liquid metals like a nightmarish forge suspended in space. And while they're cool by stellar standards, their cores are still scorching, just not hot enough to fuse hydrogen. It's like having an oven set to warm instead of broil, with just enough energy to puff up their gaseous layers but never truly ignite. The discovery of these lukewarm dwarfs forced astronomers to rethink the line between planets and stars. Before the 1990s, no one imagined objects could exist in this strange limbo. Now we know they're everywhere. NASA, a WISE telescope, has spotted hundreds lurking in our galactic neighborhood, some floating alone in the dark, others orbiting brighter stars like silent shadows. Their very existence hints at a universe far richer in variety than we ever dreamed, where the definitions of star and planet blur into something wonderfully ambiguous. Here's the kicker: brown dwarfs might be the ultimate time capsules. Because they cool so slowly, some of the oldest white dwarfs could still retain clues about the early universe's chemistry, untouched by the ravages of stellar fusion. They're the cosmic equivalent of a prehistoric mosquito trapped in amber, preserving secrets in their sluggish, smoldering hearts. And who knows, if life exists in unexpected places, perhaps these twilight worlds harbor molecules or conditions we haven't even considered. After all, in a universe where stars can be colder than coffee, anything seems possible. Gravity doesn't just keep us grounded, it shapes us from the inside out, right down to the very organ that keeps us alive. In space, astronauts' hearts undergo a bizarre transformation, gradually morphing from their efficient, elongated shape into something closer to a sphere. Without Earth's constant pull, the heart doesn't have to work as hard to pump blood upward, so it adapts, and not for the better. This cosmic cardiac remodeling was first noticed in ultrasound scans of astronauts aboard the International Space Station. Over months in microgravity, their hearts lost mass and became more spherical by nearly 10%, like a balloon deflating unevenly. The change might sound subtle, but for an organ fine-tuned by evolution to function in gravity's grip, it's a big deal. A rounder heart is a weaker heart, less efficient at circulating blood. Upon returning to Earth, some astronauts struggle with dizziness or even fainting because their reshaped hearts can't immediately readjust to fighting gravity again. The implications are staggering, especially for long-duration missions to Mars. A weaker heart could limit an astronaut's ability to perform strenuous tasks or respond to emergencies. But here's where science fights back. The ISS has become a floating gym, packed with workout gear specially designed to combat these effects. Astronauts log 2.5 hours of exercise daily, strapping into resistance machines like ODD, Advanced Resistive Exercise Device, which simulates weightlifting in zero-G. They also pedal on stationary bikes and jog on treadmills harnessed to bungee cords, all to trick their bodies into thinking they're still earthbound. What's fascinating is how the heart's plasticity reveals its ingenuity. Just as it adapts to space, it can relearn gravity's demands. Studies show most astronauts' hearts return to normal within a year of coming home, though some changes might linger longer. NASA twin study, which compared astronaut Scott Kelly to his Earth-bound brother, found his heart shrank slightly during his year in orbit but mostly recovered. Still, scientists are digging deeper, studying whether these adaptations could pose risks later in life, like premature aging or cardiovascular disease. The heart's cosmic journey isn't just about biology, it's a lesson in resilience. Every pulse in microgravity is a testament to how deeply we're tied to Earth and how fiercely our bodies cling to the conditions that shape them. As we prepare for longer voyages, understanding these changes could mean the difference between pioneers thriving or merely surviving. So while the stars might call to us, our hearts whisper a reminder: we're children of gravity, and venturing beyond it demands more than courage. It demands reinventing what it means to stay human. The moon isn't the dead, silent world we often imagine. It shakes, rattles, and rolls with tremors powerful enough to topple future lunar habitats. These moonquakes, as they're called, come in 4 distinct flavors, each more unsettling than the last. The most violent, deep seismic shudders triggered by Earth's gravitational pull, reaching magnitudes up to 5.5 on the Richter scale, strong enough to crack plaster walls if they existed up there. What makes moonquakes so alarming isn't just their strength, but their staying power. On Earth, earthquakes typically fade within minutes as vibrations dissipate through our planet's watery crust. But the moon's dry, rigid structure acts like a tuning fork, letting quakes reverberate for hours. Apollo astronauts left seismometers on the surface during their missions, and those instruments recorded lunar tremors lasting 10 times longer than anything on our home planet. Some even produced eerie, ringing signals, as if the entire moon were humming after the initial shock. The worst offenders are tidal moonquakes, born from the gravitational tug of war between Earth and the moon. Just as our oceans bulge with tides, the solid moon itself flexes under the strain, its crust stretching and compressing like a rubber ball squeezed in an invisible fist. These quakes strike about 600 miles beneath the surface, far deeper than any earthquake, and recur like clockwork every 27 days, the exact length of the moon's orbit around Earth. Then there's the thermal quakes, the moon's way of groaning under temperature swings. After 2 weeks of relentless sunlight baking the surface to 260 degrees Fahrenheit, lunar night plunges temperatures to -280 degrees. That 400-degree whiplash makes the crust contract so violently it pops like overstressed concrete, sending shallow tremors rippling across the surface. Apollo seismometers picked up thousands of these events at sunrise, as if the moon itself were waking up with popping joints. For future moon bases, these quakes pose a nightmare engineers are only beginning to confront. Unlike earthquakes, which tend to cluster along fault lines, moonquakes can strike anywhere, anytime. A colony near a so-called stable zone might still find its solar panels shattered by a pre-dawn thermal quake or its tunnels collapsed by a deep tidal shudder. Some concepts for lunar architecture include flexible jointed structures or shock-absorbing foundations filled with regolith, the same loose moon dust that blankets the surface. The deeper lesson here, the moon isn't just a static waypoint for Mars missions. It's a dynamic world with its own geologic tantrums, a reminder that even our closest celestial neighbor plays by rules we're still deciphering. Every moonquake recorded is a message in planetary Morse code, hinting at mysteries buried deep beneath the dust. And for the astronauts who'll one day call that fractured landscape home, understanding these tremors isn't just science, it's survival. A teaspoon of neutron star material weighs more than all the cars on Earth combined, roughly 1 billion tons packed into something the size of a sugar cube. Wrap your mind around that for a second. If you could scoop up just a few grams of this ultra-dense cosmic matter, it would punch straight through the planet like a bullet through tissue paper, drawn inexorably toward Earth's core by its own unimaginable gravity. This absurd density comes from a neutron star's origins, the collapsed core of a once mighty star that exhausted its fuel and died in a supernova explosion. When a star several times more massive than our Sun runs out of fusion fuel, its outer layers blast outward in a cataclysmic explosion, while the core implodes with such violence that protons and electrons are crushed together, merging into neutrons. The result, a city-sized orb so compact that a single thimbleful of its material contains more mass than all of humanity. Picture Mount Everest compressed into a raindrop, or every automobile ever built squeezed into a marble. That's the level of cosmic compression we're talking about. And the effects of this density are even wilder than the numbers suggest. A neutron star's gravity is so intense, it distorts the very fabric of space-time around it. Light from its surface doesn't radiate outward in straight lines. It bends around the star's equator like water circling a drain, creating a lensing effect that would make the horizon appear to curve upward if you could stand on its surface. Not that you'd survive the attempt. The tidal forces near a neutron star are so extreme, they'd stretch your body into a spaghetti-like strand atom by atom long before you even touch the surface. Even more bizarre is how neutron stars defy the laws of earthly materials. Their crust, if you can call it that, isn't rock or metal but a crystalline lattice of iron nuclei packed so tightly they form a solid more rigid than diamond. Yet beneath this ultra-hard shell, the interior may be a quantum playground where neutrons dissolve into a soup of free-floating quarks, or where bizarre, pasta phases of nuclear matter arrange themselves into shapes resembling lasagna sheets or spaghetti strands. Some theories even suggest the cores of the most massive neutron stars might harbor black holes in miniature, regions where matter collapses into an even more exotic state we can't yet comprehend. The real kicker, neutron stars aren't just cosmic curiosities, they're the universe's ultimate laboratories. By studying their pulses, astronomers have confirmed Einstein's predictions about gravity with precision impossible on Earth. Their collisions, detected as gravitational waves, forge heavy elements like gold and platinum, seeding the cosmos with the building blocks of planets and life. And their very existence pushes the boundaries of physics, forcing us to ask, at what point does matter stop being matter and become something else entirely? So the next time you stir sugar into your coffee, consider this. Out there in the darkness spins a reality where that teaspoon could anchor an entire mountain range, where gravity doesn't just pull, it warps the stage of existence itself. Neutron stars are nature's way of showing us how extreme the universe can get when it really puts its mind to it. And the craziest part, we've only begun to unravel their secrets. Beyond the icy reaches of Pluto, something massive may be lurking in the shadows. An unseen world 10 times heavier than Earth, slowly carving its path through the frozen outskirts of our solar system. Astronomers call it Planet 9, a hypothetical ice giant that could rewrite the map of our cosmic neighborhood. While we haven't spotted it directly, the evidence for its existence is written in the strange, clustered orbits of distant objects drifting beyond Neptune. They move as if an invisible hand is herding them, their paths tilted and stretched in ways that defy the gravitational pull of the planets we already know. The hunt for Planet 9 began with a pattern. Dozens of trans-Neptunian objects, icy bodies like Sedna and Biden share orbits that bunch together at one end, like compass needles all pointing the same way. Statistically, the odds of this happening by chance are less than 1 in 1,000. Then there's the way some of these objects swing far out of the solar system's flat plane, their trajectories yanked upward as if something massive had tugged them off course. The most plausible explanation, a distant, undiscovered planet roughly 4 to 8 times the size of Earth, looping the Sun in a wildly elongated orbit that takes 10 to 20,000 years to complete. So why haven't we found it yet? The challenge lies in its hiding place. If Planet 9 exists, it's likely 20 times farther from the Sun than Neptune at its closest approach, and up to 60 times farther at its most distant. At those ranges, sunlight is so feeble that even a giant reflects almost none back to our telescopes. It's like searching for a charcoal briquette in the void using only a flashlight. Compounding the problem, we don't know exactly where in its colossal orbit the planet might be. It could be drifting slowly through its closest approach or languishing in the deep freeze of its outermost path, making it staggeringly dim. Yet astronomers aren't giving up. Using advanced sky surveys like the Subaru telescope in Hawaii, teams are methodically scanning the most likely patches of sky, hunting for a single, faint dot moving against the backdrop of stars. Some researchers are even turning to archival data, scouring old images for traces of the planet's motion that might have been overlooked. Others suggest we might detect its heat signature with next-generation infrared telescopes, or infer its location by tracking more of the bizarre objects it seems to perturb. The implications of finding Planet 9 would be monumental. It could explain other solar system mysteries, like the odd tilt of the Sun's axis or the peculiar orbits of dwarf planets. Some theories even propose it's a rogue world captured from another star long ago, an interstellar immigrant hiding in plain sight. Until we spot it, though, it remains a ghost in the data, a tantalizing what-if at the edge of everything we know. One thing's certain, if this phantom planet is real, it's a reminder that our solar system still holds secrets waiting to be uncovered, and that the cosmic story is far from finished. From planets spinning backward to neutron stars heavier than mountains, space never runs out of ways to leave us speechless. We've seen astronauts grow taller, smelled moon dust like gunpowder, and discovered storms shaped like perfect hexagons. We've learned that tears float in bubbles, that the universe's true color resembles a latte, and that somewhere out there, a cloud floats with enough alcohol to supply every party in galactic history. Every fact is a reminder. The cosmos doesn't just defy expectations, it reinvents them entirely. What's incredible isn't just how bizarre these discoveries are, it's how they keep coming. For every mystery we solve, space unveils 10 more. Just when we think we've grasped the rules, a planet made of diamond or a star colder than coffee comes along and laughs at our textbooks. That's the magic of exploration. The universe isn't a puzzle with missing pieces. It's a puzzle that grows bigger and wilder the more we look at it. Now it's your turn. Which fact made your jaw drop the hardest? Was it Saturn's rings vanishing like cosmic sand through an hourglass, the dog that became a space pioneer? Or maybe the idea that sunlight warming your skin today was forged when woolly mammoths still roamed? Drop your favorite in the comments or hit us with a space mystery you'd love to see unraveled next. The more we share, the more we realize how much wonder is still out there waiting to be found. If this journey through the weird and wonderful reminded you why space is the ultimate adventure, don't let the exploration stop here. Hit subscribe and let's keep decoding the universe's secrets together, one mind-blowing fact at a time, because the cosmos has a way of keeping us humble, curious, and utterly dazzled. And the best part, we've barely scratched the surface.